In this video, we're going to work a bunch of graphical limit example problems. So, evaluating limits graphically. Graphical limit problems are very useful for developing your intuition behind the meaning of limits. The meaning of limits is what we talked about in this opening section on limits, the Introduction to Limits section 2.2. And so that's why we're going to work these graphical limit problems now. Okay, but now the limit problems you're probably most familiar with are limits like this, right? When you think about limit problems on a calculus test, for example, something like this is the first thing that comes to mind. The limit as x approaches a number, or perhaps as x approaches positive or negative infinity, of some expression or function of x is equal to what? And yes, of course, in upcoming sections, we're going to learn how to evaluate limits of actual functions of x like this. In fact, there's going to be an entire limit marathon video where we evaluate limits of functions like this. Okay, but it's not like once you've gotten really good at evaluating graphical limits like this, then that means you can easily just come to the limit of a function like this and evaluate it. Okay, but the main reason why you're not able to, after you really understand graphical limits, and so you have a very good intuitive understanding of what the limit means, the reason why you're not able to just come to a limit problem like this and easily get the answer is more from a mechanical standpoint. Like, what I mean is that there's tips and tricks we need to understand in order to figure out what the limits of different types of functions are. Ways we need to potentially algebraically manipulate certain expressions, for example. Okay, but outside of mechanically, once we're really comfortable with graphical limits, we will be able to come to a problem like this, look at a limit like this, and understand what this means. It'll be very clear what this is saying because any function like this is going to have a graph, right? And so you've got the limit as x approaches 16 of this graph is equal to some number. We'll understand exactly what all of that means. And so it really just comes down to the mechanics of dealing with limits involving different types of expressions is what we're going to have to learn in order to be able to evaluate limits like this. So, okay, let's get started. It says, so use the given graph of the function f to state the value of each quantity if it exists. If it does not exist, explain why. So, okay, what is the limit as x approaches 2 from the left of f of x? So here's f of x. As x approaches 2 from the left, so we're approaching 2 from just the left. We don't care about what's happening coming from the right. Well, okay, we can get as close as we possibly want to 2 coming from the left. So 1.999, a trillion nines. And if we plug that into f of x, we're going to be getting some number that's closer, some output that's closer and closer and closer and closer to 3 coming from above 3. Like 3.000, a trillion zeros, 1. So this limit is equal to 3. What about x approaching 2 from the right? Okay, well, look, we have an open circle here. So the function f of 2 itself, the function evaluated at 2, does exist. It's equal to 3. So does that come into play here? Since the function evaluated at 2 is not equal to this, whatever this value is? Well, no, absolutely not. When evaluating limits, we do not care whatsoever about what the function is doing at the limit value itself. All that matters here is that if we had some super powerful calculator and we could plug into this function like an insanely close number to 2 coming from the right of 2, 2.000, or trillion zeros, 1, we would plug that into the calculator to f of x. What would we see the output approaching? If we kept getting closer and closer and closer and closer to 2, we would be approaching 1 coming from above 1, right? 1.000, or trillion zeros, 1. It doesn't matter that whether or not we're coming from above or below the output. I'm just stating that for clarity, right? If we were coming from below 1, we would still write this limit as this is 1. Okay? Now, what about the limit as x approaches 2 in general? So this is not a one-sided limit. Well, okay, in order for a limit to exist in general, you need to be approaching the same output value coming from both sides of the input that's specified. And in this case, we're not. Coming from the left, this is approaching 3. Coming from the right of 2, the function is approaching 1. So there's not this single unique value, so this limit does not exist. Okay, what is f of 2? The function evaluated at 2. So this has nothing to do with limits, but they're just asking us this as sort of kind of like a trick question, you could say. Because, I mean, this is all about limits, right? But really this has nothing to do with limits. The function evaluated at the limit, or at the value you're specified to be approaching. Okay, well, f of 2 we can see is 2 or 3. But as we talked about, this could be equal to nothing. The function could not exist here. This could be equal to a unicorn. It makes no difference whatsoever in regards to what we did here in parts A, B, and C. Okay, what is the limit as x approaches 4 in general of f of x? Well, okay, coming from the left and coming from the right, we're approaching the same value, 4, the same output value, right? Now, but wait a minute, the function doesn't exist at 4. F of 4, there is no output. Doesn't that factor into this limit? 100% no, because we could plug in f of 3.999 a million zeros 9, we'd get something right below 4. 3.999 a trillion zeros 9, we'd get something right below 4. It would be getting closer and closer and closer to 4, and then if we plugged in f of 4.000 a million zeros 1, we'd be getting an output that's right above 4. 4.000 a million zeros 1. 4.000 a trillion zeros 1 is the input. The output is 4.000 like a trillion zeros 1 again. So we're sandwiching the value 4. Okay. This is f of x. What is the limit as x approaches 1 in general of f of x? So as x approaches 1, here's 1. So, okay, coming from the function exists here, but that doesn't matter. Coming from the left, we're approaching 2. Coming from the right, we're approaching 2. So this is equal to 2. What about as x approaches 3 from the left? So here's 3. Coming from the left, we could get extremely close as we want to 3 on the left side of 3, 2.999, a quintillion nines, and we're going to be getting closer and closer and closer and closer to, we can see 1. Okay, what about the limit as x approaches 3 from the right? Well, we're approaching 4. From below 4, but again, above or below doesn't matter. I'm just stating that just to give you some intuition. What about as x approaches 3 in general? Well, we're approaching 2 different values coming from both sides, so this doesn't exist. Okay, now what is f of 3? This is like a trick question. F of 3 we can see is 3, and how does that factor into the limits we just evaluated as x approaches 3? It doesn't. F of 3 could not exist. F of 3 could be 10. F of 3 could be equal to unicorn. It makes no difference whatsoever as far as the limits we just evaluated around 3. Okay, what is the limit as, this is h of x. What is the limit as x approaches minus 3 coming from the left side of minus 3? So we're approaching 1, 2, 3, 4. What about coming from the right of minus 3? We're approaching 4 from below. Now, minus 3 in general, so coming from both sides, we're approaching 4. And we talked about how you might say, well, no, we're not sandwiching 4, right? We're not coming from one side, we're approaching 4 as the output from above, and coming from the other side, we're approaching 4 as the output from below. That doesn't matter. All that matters is we're approaching we can get infinitely close to -3 on both sides, and the output is, on both cases, is getting closer and closer and infinitesimally closer to the same output value, which in this case is 4. What is h of -3? It doesn't exist. There's no output here, which again has absolutely no effect on what we just did with these limits at 3. Okay, what is the limit as x approaches 0 from the left of h of x? That is 1. What about the limit as x approaches 0 from the right? That's -1. What about the limit as x approaches 0 in general? That doesn't exist. We're not approaching the same value on both sides. What about h of 0? We can see that's 1. Okay, what is the limit as x approaches 2? Well, okay, coming from the left and coming from the right, we're actually sandwiching the output in this case, which doesn't matter, but we're approaching the same value coming from the left and the right, which is 2. Now, what's h of 2? This doesn't exist. But h of 2 could have been 4, and that wouldn't have had any effect on this limit here. Okay, what is the limit as x approaches 5? Coming from the left and coming from the right. So what they're going for here is, we looked at an example of, there was a sine function. It was like sine of x divided by x, I want to say. Is that what it was? Or no, it was sine of pi of x. It was sine of pi of x. And as the limit as x approaches 0 of sine of pi over x, and as you get closer and closer and closer and closer to 0 coming from either side, it's just always still oscillating between 1 and -1. You're never honing in on a specific value as you get for that function, as you get closer and closer and closer to 1 and or to 0 from either side. And that's what they're going for here. That's what they're trying to illustrate here. When we're approaching 5 from the left, no matter how close we get to 5, so we could plug in 4.999 a million zeros 9, and we might get 2. Then we can plug in 4.999 a trillion zeros 9, and we might get 4. And it just continue to oscillate no matter how close we get to 5 coming from the left. So this doesn't exist. Okay, now coming from the right, this will exist. The reason is because no matter how close we get to 5, coming from above 5.000 or trillion zeros 1, etc., we're never going to enter this oscillating region here. All we're going to be doing is, you'll have 5.000 a million zeros 1, and then you'll get something like 3.000 a million zeros 1. If we input 5.000 a trillion zeros 1, we'll be getting something like 3.000 a trillion zeros 1. Right? We're approaching 3 here. Okay, the limit as t approaches 0 from the left, so we're approaching -1. As t approaches 0 from the right, we're approaching -2. As t approaches 0 in general, this doesn't exist. Okay, as t approaches 2 from the left, we're approaching 2. As t approaches 2 from the right, we're approaching 0. As t approaches 2 in general, this doesn't exist. Now, g of 2 we can see is equal to 1. All right, now what about the limit as t approaches 4? This is kind of tricky, right? We don't have any weird-looking discontinuity or a hole here. So what? So we're thinking about t approaching 4 in general, so we need to analyze both sides. Okay, we're getting closer and closer and closer to 4 coming from below 4. Well, okay, what are we approaching? If we plug in 3.999, a million zeros 9, we're going to get something right below 3. 3.999, a trillion zeros 9, something even closer to 3 from below 3. We're approaching 3 coming from the left of 4. Coming from the right of 4, we're approaching 3 from above. This is 3. Okay, this is the function a of x. So what is the limit as x approaches minus 3 from the, in general? Okay, so coming from the left, this is an infinite limit, right? The closer and closer and closer we get to the minus 3 coming from below, we're just going to get larger and larger and larger and larger and larger numbers. The idea is we can specify any number we want. If we had an infinitely powerful calculator, then I could give you any number I want, 500 quintillion, any number I want, no matter how large it is. In this case, be a large positive number. And given that number, I could say, okay, I can plug into the function something that's close enough to 3 from, just below 3, minus 2 or minus 3.000, whatever, however many zeros 1, and I'll give you a number that's right around the magnitude of that number you gave me, assuming we have like an infinitely powerful calculator, right? Now, same idea coming from the left. We're also, the positive side of minus 3, we're also approaching, as x approaches minus 3 from the right, the function is also approaching positive infinity, so this is positive infinity. Okay, as x approaches 2 from the left, the function is approaching negative infinity, but yeah, and that's all they asked for, just 2, as x approaches 2 from the left, this is approaching negative infinity. 2 from the right, positive infinity, and as x approaches minus 1 in general, so we have to analyze both sides, they're both approaching minus infinity. Now, okay, what are the equations of the vertical asymptotes? What did we talk about was a vertical asymptote? It's the equation of a vertical line, which is going to be like x is equal to some number, as long as there's just on just one side of the vertical line, or both, whatever. If there's just one infinite limit associated with that vertical line, that's going to be a vertical asymptote. So here we've got 3 vertical asymptotes. We have x is equal to minus 3, x is equal to minus 1, and x is equal to 2. Okay, but it just so happens that both sides of these vertical lines have these infinite limits associated with them, but all there would need to have been is just one side have a infinite limit associated with it, and you'd call that a vertical asymptote. Okay, what is the limit as x approaches minus 7 of this function? So coming from both sides of x equal minus 7, this function is approaching negative infinity. What about negative 3? The function is approaching infinity from both sides. What about as x approaches 0? The function is approaching infinity from both sides. What about as x approaches 6 from the left? The function is approaching negative infinity. What about as x approaches 6 from the right? The function is approaching in positive infinity. And so now they don't ask this, but what would the limit as x approaches 6 in general be of f of x? Well, that wouldn't exist, because we can't, all of these don't exist. An infinite limit technically doesn't exist, right? Because like it's not a specific number, but we just express these types of limits that don't exist. We can put the infinity symbol like this. Here we have to literally put the d and e. We can't even use an infinity symbol here for 6 in general. Okay, now what are the equations of the vertical asymptotes? That's going to be x is equal to minus 7, x is equal to minus 3, x is equal to 0, and x is equal to 6.